2, 1. Respect. Very good. Hey, nice to be back. So it's already our third lecture of the season. So we're in a good speed already. And today is going to be the first lecture that is going to be involving, mathematically involving. So it's going to be something that is not going to be as pleasant as lectures so far. So we're going to look things that are a bit more involving in terms of partial differentiation. It's going to be still doable, something that you will understand well. And I will give you the few hints how to handle the mathematics involved today's lecture. And then what comes after that is that if everything goes like in a movies, which I doubt, we are able to close the case, which is called kinematic analysis. Remember, the kinematic analysis is all about the motion, it's art of motion. It's not related to forces. Kinematics is not telling you anything about the forces because it's based on the constraints and motion. That's what it is. Basically, what I wanted to say that is based on constraints and driven constraints. The ones that are giving the motion and other ones that are limiting the motion possibilities. And this is something that we can solve if we have matching number of equations and unknowns. We already learned that the unknowns are generalized coordinates. And we learned from the last week that every body needs 3 generalized coordinates. All right? So that's something that is a number of unknowns associated with each one of the bodies we have in a system. So if you have one body, you need 3 unknowns. If you have 2 bodies, you need 6, so on and so forth. So every body adds 3 generalized coordinates, 3 variables. And these variables telling you how is that this configuration of the system at any given time. Now the constraints are the ones that are limiting the motion possibilities. Like mentioned, if you know all the constraints, then you can conduct something that is called kinematic analysis. Okay, but we're going to summarize what we discussed a week ago momentarily, but we need to get started something a bit more practical. A bit more practical is related to first midterm exam. It will be organized in week 43, and it will be in model. It will be in model. So we've been testing back and forth with the different kind of AI systems, see how well the ChatGPT is doing, if asking ChatGPT to do the midterm exam, and you can imagine how well it's doing, because otherwise we would not do this in online exam. So the ChatGPT, thanks God, is a bit clumsy what comes in a certain kind of the mathematics, and that's a good news, because I'm going to have quite a bit of mathematics in my midterm exam. Now how this goes, during this week 43, you have 2 attempts. Highest will be accounted. And I highly recommend that you do your first attempt beginning of the week, whatever time is convenient to you. You just basically need to log into Moodle database with your own student ID numbers and whatever is the way that you do your logging. And then you just click that Get Started with the exam. And once you click this, there's no way back. I mean, that there's of course a way back if you invented a time machine and go back in a time. But if you don't have a time machine, then you just have to do the exam. That's it. And then you will have this, I think it is 2 hours or 3 hours. This is what I'm not 100% sure time. That's much time that you can complete the exam. Then you click submit and you can automatically see your scoring. And if you're not happy with your scoring, then within this week you will have another attempt. And the highest, again, will be accounted. Now here comes something that is important. Each of the weekly assignments, we have a serious doubt that many of you are not solving those by using your own mathematical skills, but using the mathematical skills of ChatGPT. And it's going to be making your life difficult in the midterm exam. So what I'm proposing you to do from this on is that you start building kind of like a library for different kind of weekly assignments. And the weekly assignments is like, okay, how to describe the particle position. And then you just do the submissions and you will gonna get the correct answer more or less automatically with your symbolic math tool. So now what you need to do is that you need to pick a symbolic math tool, whatever is your preference. So if you like, MathCAD, fine, use that. If you like MATLAB, use that. If you use a Maple, like that's my preference, use Maple. So whatever tool you wanted to use, but start building the library to yourself, because this library becomes to be extremely handy once you enter your midterm exam. Okay, so that's how it's gonna go. And was there anything, other things that is significant in terms of midterm exam? Well, not really anything else, except that there's going to be a 7th lecture of the season, which is going to be summarizing whatever I'm expecting you to know whenever you go the midterm exam. Okay, but in the math tool, what comes to be necessary, particularly after today's lecture, is that you need to do automated differentiation, like partial differentiation. You need to be able to tell, okay, here's a one vector, here's another. I want to conduct this vector with respect to this vector using partial differentiation. This is something that all the math tools can conduct it. It's just have a different names in their procedures. Sometimes called Jacobian, sometimes something else, but make this to be automated, because that's one of the questions will be asked in first midterm exam. Okay, how this sounds? You guys love me now because the exam is in a Moodle, or is there a love in here, or we should speak about more about bodies and constraints and stuff? No love. There's a love. There's a love. Okay, Team Asia is loving here, so it's really good. It's promising. Team Finland?
It sounds good.
Sounds good. Oh, they are respect. They're in a respect level, so they beat you guys. So Team Asia need to figure out better than that. Okay, good. So that's a big plan. Again, we will get back to the details in week 7. So we have still a few weeks to go. If I take myself back here, we're here. So this is our 3rd week. Today we're going to cover the materials related to kinematics. And then next week on, we're going to discuss about the forces. So far, nothing whatsoever about the forces. And then all of a sudden, we're going to start discussing about the forces. And already this time, it's good you to be aware of that what we're going to do here is that we're going to express all the forces in terms of our variables, generalized coordinates. That's why the names that you can see here are like generalized inertial forces, meaning that the inertial forces, this one will be expressed in terms of generalized coordinates. And the same for external applied forces and so on and so forth. So that's what's going to follow. But again, no forces from this part of the lecture. Good. This is what we discussed. That's what we discussed a week ago. So we discussed about how is that we can describe the particle with respect to reference coordinate system, often called as global coordinate system. And we do that with the help of body reference coordinate system. So first we're going to go to origin of the body reference coordinate system by using a vector r. And then we're going to take the body orientation of the body reference coordinate system into account. That's going to be the 2x2 matrix in case of planar case, 3x3 matrix in spatial case. And then with help of u bar, we're going to reach wherever the position P, particle P is located at. Okay, this is something I think that I mentioned earlier, but keep in mind that if you form a vector out of the columns of your rotation matrix, this vector or these two vectors will be perpendicular with respect to each other, meaning that they're going to form a 90 degrees angle with respect to each other. And they are unit in the length. This is a definition of orthogonality in mathematics. So this matrix is orthogonal matrix, meaning that its inverse is simply you can get it inverse by transferring the matrix. Okay, so that's how it's going to go. We also looked at how is that you can do the rotations in 3-dimensional space. In spatial case, a little more challenging. And we learned the one method, and one method only, that was based on Euler angles. We also learned that many of their software, particularly the modern software, are not based on 3 parameters. They're not, but they're based on 4 parameters, typically called as quaternions. 4 parameters are not independent, but they are dependent by one constraint equations. That's something that is for your information this time. If you want to learn more, there's a bunch of books about rotations and quaternions. Not because of mechanical engineering, but mainly because of aerospace application. There are rotations in aerospace application. Outer space particularly is very, very important. And if you want to entertain yourself, you want to take a look. You might want to take a look at these Euler angles and something that is called gimbal locking. Gimbal locking is a story like how you can lose your ability to understand the rotations, which can be critical in outer space application. I think they're explaining this. Some of these YouTube channels are explaining those gimbal lockings in terms of different kind of like accidents that happens outer space. So check out. All right. Anyways, back to these Euler angles, where the concept is based on 3 successive rotations. That means that there's one rotation after another, and the third rotation takes place twice rotated coordinate system. So the first rotation, typically, this is a typical way, is taking a place around z-axis. Amount of rotation is, how you call this? Was it T? P. Phi. Phi? It's phi. All right. Anyways, so you have an amount of rotation that is this one, and then the next rotation takes place around once rotated x-axis. Amount of rotation is theta, and then theta. Yes, correct, theta. And then the one more rotation takes place twice rotated z-axis. Amount of rotation is c. Okay, very good. And then you're forming 3 by 3 matrices describing each of these rotations, and final form of rotation you can get it by multiplying these matrices together. This is how you counting. This is how you describing successive rotations. All right. So hold on. So just to get back here, there was an example. Okay, so body rotates 90 degrees angle, which is, of course, we need to express this by using radians. So it's going to be p divided by 2, and it takes a place around, obviously, x coordinate axis. That's going to be simple, because x is the one that we actually have the rotation. Amount of rotation that takes a place around the x-axis was this theta. So basically what you need to do is that you need to substitute that information to this vector. This is going to be 0. This is going to be, where is it? This one, p divided by 2. This guy is going to be 0. You do the substitution and you do the math. This is how your 3 by 3 rotation matrix reads. Now they often ask questions like, oh yeah, but this you cannot use this because you do not have a rotation around y coordinate axis. So no one could use this method. Now if you would have a rotation around, like say that the v vector would be 0, 1, 0, which is obviously y coordinate axis. And let's say that the rotation would be, let's say, p divided by 4. 45 degrees. So how you would do that? So first what you need to do is that you need to replace the axis of z and y coordinate axis. So you need to first introduce the rotation that is p divided by 2. I'm going to show this graphically here momentarily. Then you do your rotation, and then you need to compensate the first rotation, which is going to be minus p divided by 2. So then you need to use each of these 3 parameters. Let me take you back here, which is this graphical representation. So first what you need to do is that you need to have this rotation 90 degrees, p divided by 2, to make your x-axis pointing this direction. This is where the original y-axis is located at. Then you do your rotation, which is this, I think I mentioned p divided by 4, which is theta p divided by 4. And then you need to recompensate. You kind of get back to the system where it gets started. You need to compensate that by putting this to be minus p divided by 2. And that's your y coordinate rotation. You got it? Yes, sir.
So for the first example, if x must be 45 degrees, then
yes.
Do we have to relate it by 90 degrees?
So if the x is 45 degrees, yeah, then the only thing you need to do is this. You just need to convert this to be 45 degrees, which is a p divided by 4.
Because it's only rotated around x.
Yeah, because it's a positive rotation, and that's it. Nothing else, nothing else. But the second example was more complicated because we're missing the y-axis, kind of missing. So what we do is that we put the x-axis in a direction of y-coordinate axis, we do the rotation, and then we put it back. And that's it. You were still following me? Yes. It's okay. Everything is good. Life is good. It's Monday. I know that it's not Friday, but still life is okay. Good. All right. Tips for weekly assignments. First tip is use symbolic math tool. Build the library by yourself because this is a way to successful midterm exams. And don't trust to ChatGPT because we tested. We tested. And we would not use a Moodle exam if we know that it's going to score well. So it's actually struggling quite a bit, which is great. Great news. All right. Now be careful with the radians degrees when you're using trigonometric functions. I think that most of the settings are radians. So you need to be very, very careful with that. And then if you need any help, there's a Mustafa that can help you. Okay, moving on. So I need to speed up a little bit. So this also what we discussed a week ago. So we discussed about velocity and acceleration. So these are the kind of like mechanical things to get because the only thing we need to know is how you're describing a particle with respect to reference coordinate system. And we have created that is this one. This is our kinematics. And now what we do then is that we differentiate this with respect to time. So we're going to take this one, differentiate that with respect to time. That's going to be your velocity, and the velocity can be written like this. This one here is angular velocity. All right, this is something that is rotated 90 degrees angle with respect to original configuration, and this is vector u bar. When you differentiate it another time with respect to time, that's what you're going to get. So now you have here translational velocity, you have normal acceleration component due to the angular velocity, and tangential acceleration component due to the angular acceleration. All right, these were the components. And then we discussed about constraints. Now, constraints are the ones that are in real life are joints. And joints are limiting the motion possibilities. And this is exactly what I'm referring when I'm explaining about the kinematics. So kinematics is the art of motion. So if I take a hold of this piston part, and I'm saying the piston part, you need to follow the following equation. Sine equal to time. So meaning that it's going to make a sinusoidal motion like this. So the piston will go back and forth because of that. Then I can solve the entire system because I know the constraints. I know that there's a revolute joint here, there's a revolute joint here, and there's a revolute joint here, and there's a translational joint that combines the piston and the ground. That's all I need to know. Nothing but this information. And then this is going to give me the equal number of unknowns and equations. What are the unknowns? Those are tenuous coordinates. Now here I have 1, 2, 3 moving bodies. So how many tenuous coordinates? 3. Okay, so 3. Any other proposals? This system, we're looking this system. How many tenuous coordinates we have in this system?
9.
So, okay, then there's a 9. Any other proposals? So we have already people that are saying that it's going to be 3, 9. Anything else? 9. Okay, which ones you guys are voting for? So which one you like more? So which one is the correct answer? Is it going to be 3 or it's going to be 9? Okay, all of you need to cast a vote. So it's going to be, how many of you are voting for 9 tenuous coordinates? 9. I say 9. Yeah,
9.
This one. You're voting this one? How many of you are voting 3? 0. Okay, fantastic. That's a great news because everybody needs 3 tenuous coordinates. But here we have 3 bodies. So it's not the single body, but 3 bodies. And that's why the 9 is a correct answer. All right, that's how many unknowns we have. So that's a number of unknowns in total, 9 unknowns. Okay, let's take a look at how many different kind of the joints I have here. So I have here revolute joint, revolute joint, revolute joint. That's going to be a total of 6 constraint equations because of that. Correct. Because 3 revolute joints, each of them having 2 constraint equations. So that's total of 6. And then I have here 1 translational joint, that's going to be additional 2. That's going to be 8. And the number of degrees of freedom is going to be 1. Now, if I take a hold of this 1 remaining degrees of freedom by introducing this driven constraint, then I have 1 more constraint here. And number of degrees of freedom becomes to be 0. So then I have matching numbers of unknowns and equations. This system is called kinematically driven system. Kinematically driven because all the solutions, all the responses, all the life, the velocity, position, acceleration is given by constraints, nothing but constraints. This is conceptually different, altogether different than dynamically driven system. This was a kinematically driven, again, because of this remaining degrees of freedom. And it doesn't matter where you're going to impose this driven constraint. You can put it in a joints, you can put it in, anywhere you want. You can put it in this joint or you can put it here, but you're just introducing additional constraint. The ones that is a function of time called as a driven constraint. All right, this system here is different because this is driven by moment, which is a force. There's 1 degree of freedom in a system, and this 1 degree of freedom is actually applied or make it to move by force. This is something that you cannot solve by any other means but creating the equation of motion and solving the equation of motion in forward of time. That's what it is. All right. Kinematically driven system, kinematic system is where the number of degrees of freedom is 0. Matching number of unknowns and equations. Makes sense? Makes sense? Yes, sir.
Does it mean the first one was the constant speed?
So this is something that is this is a constant angular velocity. Yeah, so it's rotating. This body here is rotating with a constant angular velocity. That is correct. That's a good observation. Then the rest are following this motion. The velocity, if you look at the motion of the piston part, so it stops here and, in both ends of the motion. So it's having the wide range of the position, velocity, and acceleration, as is the case of this connection rod as well. All right, good one. All right, so let's, okay, one more time. Over constraints, there's too many constraints. Then there's a kinematically driven, dynamically driven. My in-class quiz is going to be momentarily. I'm asking how is a kinematically driven system? Clear? All right. And this is how you compute the number of degrees of freedom. So it's unknowns minus constraint equations. Pretty simple math. So it's not too complicated at all. Okay, my in-class quiz is this. The number of degrees of freedom in a kinematically driven system is number of degrees of freedom now have to be negative, equal to 0, positive, more than 100. More than 100 because you better play safe. Bigger the better concept. Is it the bigger the better concept, or is it something a little different than that? Okay, is it the in-class quiz on? Can you lock in? You guys lock in? You enter your answer already? Okay, I'm not gonna stop here in my talk. I'm gonna get back to this momentarily. Okay, good, clear. All right, then I have another in-class quiz. You need to look at this. So you need to look at, how many moving bodies you have here. Then you need to remember how many constraints are needed for different kind of the joints. And for just to refresh your mind, primitive joint is something that is like the constraint point is moving within the slot. So this can slide left and right. This body can rotate like this, but it cannot go in this direction. So it's constraining 1 degrees of freedom only. So it requires 1 constraint equations only. So this kind of primitive joint, so it's one constraint equation, not more than that. Okay, now I'm gonna log out from, just a second, I'm gonna take a look how we're doing in a in-class quiz. So here, I don't wanna show this one, but I wanna take a look at this one. Okay, so we have 84 students and the success rate of the first in-class quiz must be 100%. If not 100%, guess what? We're gonna go back and we will do this until we're gonna score 100%. And I don't mind. It can take tomorrow morning or even tomorrow whole day, full day, but we need to score 100%. Ready? We can always round it up. Good news. There's a good news because there have to be a black sheep. Always there have to be a black sheep, and that's fine. That's fine. But materially are doing really well, really well. So you can give some credit to yourself. One person cannot. But other than that, we're doing fine. Okay, this one. Please help me. Please compensate the mistake we did. I mean, somebody did, not you, of course, but score here. You need to take a look what exactly is the mechanism. So let me take myself back here. This one. All right. First, compute how many unknowns. How many unknowns? How many moving bodies in this system? Okay, so yeah, if you're convinced that that's the number, then multiply the number of moving bodies by 3. That's going to be the number of unknowns. And then you need to look at how many different constraints, how many constraint equations you have to have. So then you need to look at how many revolute joints, how many primitive joints, and that's it. Okay, and the options are that there is going to be 0, 1, 2, 3. Clear? All right? You guys done? Yes. It's clear. It's very simple. Still pretty simple. All right? So a little bit about naming business. Don't try to memorize this. I don't think it is important at all. But for hardcore students, the ones that I really wanted to learn everything and more, for your information, there are different names about different kind of constraints. There are holonomic constraints that they're pretty much what we are speaking about this course. So there are revolute joint, translational joint, primitive joints, and so on and so forth. They're not functional velocities. They are basically something that is limiting the motion possibilities, position possibilities. Then we have this non-holonomic, which is pretty common too in multi-body dynamics. Those are like rolling without slipping. Like if you want to model the bicycle, then it really makes sense to use a non-holonomic constraints. So then you can model how is a tire with respect to ground. So it can roll without slipping. And you can do that in a three-dimensional space. Scalenomic is going to be the driven one, the kinematic ones. They are time independent. So typically the ones we're dealing. And reonomic is as driven. They are function of time. Like we mentioned that the x was like sine time. This is going to be reonomic driven constraint. Less important stuff. Less important. Okay, shortly. Let's take a look at this briefly and then we're going to move on. So what happens? How many different constraint equations you need in different scenarios in three-dimensional space? These are the most commonly used joints. So we have here a translational joint, revolute joint, cylindrical joint. Translational needs or constraints 3 rotational possibilities and 2 translational possibilities. So that's a total of 5 constraint equations. Correct. And then the revolute is going to constrain 2 rotational motion and 2 translational motion. So it's going to be 4. And then revolutes, so it's going to be 5, like a translational joint, so on and so forth. You can also use something that is called primitive joint, which is like a combination of different kind of joints, because the previous table wasn't full. So there may be need some special kind of constraints, which you cannot combine using these traditional ones. But you can combine that using these primitive ones, and that's how you can get the full matrix. That's basically for your information. Now comes something quite surprising. Now, let's take a look at the door that is in the back of this lecture room. And let's take a look how many degrees of freedom we're going to have in our door. So we're going to constrain the door to ground by using revolute joint. All right? Revolute joint, again, you need 5 constraint equations. Let's assuming that this door that is shown here is in a spatial case. So it's in a 3-dimensional case. So this door needs 6 generalized coordinates because it's a spatial problem. And then I have here revolute joint, so it's going to be 6 minus 5, so it's a 1 degree of freedom. Makes sense. But when I take a look at the door here, this is not how they're constructing the door, because usually there's if not 3, at least 2 revolute joints. So let's compute what's going to happen in this case. We have how many generalized coordinates? 6. Then I have here 1 revolute joint, another revolute joint. That's going to be minus 10, minus 4, minus 4. What is this minus 4? Let's go back here. Where is it? Here. And we are not able to go out from this lecture room because, it's mathematically proved over constraint. This is it. Rest of our life is going to be in this lecture room. So those of you that are lucky enough, they're following the lecture online, so they can still go, they do whatever they want. We are doomed to be here rest of the life. Everything went correctly, or is there any doubts? Have you ever used the door? Is it still operating well, or because obviously based on the math we just did, it's over constrained, and you cannot use the door. Let's look what happens if there's a 3 revolute joint. This is going to be really, really bad. So it's going to be minus 9. Oof, no way it works. No way. What explains this? Explanation is this. The constraints, they only take degrees of freedom away if the constraints are independent. What these 2 guys are doing, they're constraining exactly same generalized coordinates. So these guys are not independent, but they are dependent. So it's the same that I'm going to set the, 10 revolute joints in this same location. They are not constraining different kind of the motion, but the same motion over and over and over again. And because of that, they are not independent. This is a redundant constraint. Most of the, if not all, the commercial software can automatically recognize a situation like that. It automatically eliminates the redundant constraint. Problem is that you can also compute the reaction forces based on the constraint, and those will be maybe incorrectly computed because you really don't know how these constraints are eliminated. So it's not the good modeling practices to go minus something. But it happens really easily, really, really easily. This is a screenshot from the lecture note, which I hope that each of you already printed out and keep with you all the time. Okay, it says independent constraints, so it have to be independent. Maybe you missed this when you were reading my lecture note. Were you reading my lecture notes at all? Did you print it out? You don't need to print it out if you have an iPad, so you can read it through your iPad. But anyway, so this is what was mentioned in my lecture note. All right, let's make another example here. So here's a 4-bar mechanism. So this again, three-dimensional space. This requires 6 generalized coordinates. This is 6, and this is 6. So it's going to be a total of 18 unknowns. 18. Okay, 18 unknowns. I have here 1, 2, 3, 4 revolute joints. Each of them needs 4 constraint equations. That's going to be minus 20. Minus 2. Too many constraints. So this is our constraint system. Simply because the motion in this transverse direction is over constrained. You don't need this many. You just simply could release one of these revolute joints and put the primitive joint there instead. And then you end up to have a positive number as a modeling trick. All right, let's practice a little bit more. this is something that we're gonna get back while we're discussing about the kinematic analysis. All right, I have here one simple body that is constrained by using two primitive joints. The one joint is located in a point O, another one is in a point P. Point P is amount of E from the global x coordinate axis, whereas point O is going to be amount of D away from global y coordinate axis. So this distance was D. Okay, and now the assignment is this. Please build the constraint equations that are describing this particular system here, how we can make it happen. So here is a motion limitation, this is a motion limitation. So what we need to do is that we need to make a use of the only equation we are familiar with. This good friend of ours. We need to travel from here, the body origin of the reference coordinate system, to origin of the body reference coordinate system. And then we need to reach out the point P or point O, and then we're going to constrain it. So we are limiting the motion possibility at that particular position. That's it. That's all we need to do. How that sounds? Like a pretty much, yeah, doable. Very much doable. All right, so first comes O. So I'm going to describe the particle, this point O, by going here. Excuse me, going here first. And then this is going to be the first component, and then I'm going to move to this point here, and I will take a rotation of the body reference coordinate system into account by using 2x2 rotation matrix. The only difficult part is here that I need to define how is my vector u bar. Look how is that body reference coordinate system. Y is pointing transverse direction. X is pointing axial direction. So how much I need to move in axial direction to reach this point? That's going to be the length divided by 2. Oh, sorry, I'm in the wrong place. Here, L divided by 2, positive direction. How much in the transverse direction? 0. Because I'm already here, I'm already oriented as a body reference coordinate system, so I don't need to move in this direction at all. That's why the 0 is coming here. And then I have to do the final thing. I have to introduce the constraint here. The constraint is such that this distance along the global coordinate axis x have to remind amount of d. So I have to substitute here d. And then I do the math. I'm going to take this component, multiply this by this, and I set that to be d, and I'm substituting the d to left-hand side of the equation. That's going to be my first constraint. Simple, isn't it? Ridiculously simple. Okay, Team Asia is doing like this. Are you guys, how is it Team Asia? What is your silent sign? Is it like this, or more like a little minor level of confusion, but it's still okay? Team Finland, very confident. I figured this out already a while ago. All right, very good. Okay, good. Can we continue? Yeah. Then P, same story, but we're gonna go this point here. We're gonna go this point. So we're gonna take a use of this R vector. And then we're gonna take a rotation matrix into account, and then we need to travel the negative direction of the x coordinate axis. Negative, because the positive is pointing downwards. So this is where the minus L divided by 2 is coming from. And how much in the transverse direction? 0. Again, I have to constrain this. This time, this guy is limited in a way that this distance, y coordinate axis, have to be E all the time. Then I do the math. I'm going to take this guy here. I'm going to take this one. And I'm going to set that to be E. And E will be substituted in the left side of the equation. That's my second constraint equation. Is this system kinematically driven or dynamically driven? Okay, so who is voting for kinematically driven? How many votes I'm going to collect kinematically driven? Who is saying that this is kinematically driven? So we have how many votes? A few votes. How many are saying that dynamically driven? You have to cast your vote. You have to vote. You have to vote. This is not voluntary, but this is mandatory to vote. So most of you guys are saying dynamically driven. Correct answer is dynamically driven. Why? Because number of degrees of freedom is not 0, but positive. Why is not 0? Because I have 3 generalized coordinates, because everybody needs, yes, log and 3 generalized coordinates. So then 3 generalized coordinates. How many constraints? Well, I just computed. 2. 1. So is a 1 degrees of freedom left, and this 1 degrees of freedom can move however it wants. This 1 degrees of freedom is actually a misleading way to say, because it's a one way that the system can move. The one way is like, okay, it's a little hard to describe it, but you figure it out. You got it, right? You understand how it goes. So it's like this, yeah, you understand this, right? Okay, good. That's what I was thinking. Constraint equation. This is hard. What is it the constraint equations are doing for you? They are interconnecting generalized coordinates. They connect the generalized coordinates. They define the center of the mass of the body. They define the physical dimension of the body. And my favorite, they define the particle rotation. Now there's one thing you're not allowed to select. Otherwise, I'm gonna cry. Seriously, I'm gonna cry if you're gonna select one that is my all-time disfavorite. You just cannot select that. Please, please. You don't want to see the big man like me crying here in front of the class. Please. So can we play in the same team that much? I understand that you're a little bit on different teams, but yep. Okay. Good. So I'm gonna take myself here. Circle there. All right. First one. How is going to be the success rate of this? This is not easy. This was a little difficult. Should we go and take a look at the mechanism one more time? Yeah, okay. Let's take a look at the mechanism one more time. So this is what we discussed. Where is it now? This one. Okay, how many moving bodies? It's going to be 2 moving bodies. So that's a total of 6 generalized coordinates. How many constraints? How many revolute joints? 1, 2. So that's 2 multiplied by 2, that's 4. And 1 primitive joint, that's 1. So the number of degrees of freedom is 1. Okay, and now we're going to see how well you do. Okay, so majority are doing this correctly. There, some of you are thinking that it's going to be a 0. Some of you are thinking 2. That's like 2 moving bodies, but that's not what I asked. And some of you are thinking 3 as everybody needs 3 generalized coordinates. Maybe I have repeated that too many times. That's possible. Okay, then the next one. This is so difficult that you guys have no chance. No chance. Your success rate is going to be low, like 15%, 15%, 25%, because that is statistically what you're going to score. 25%.
You promise to cry with a gift?
Yeah, I'm going to cry if somebody is selecting something that I hate big time. Because, this class, you're already master level students and you don't believe Santa Claus anymore. You just cannot. You just cannot, because it's not existing in the real life. The same thing, the one option is the same thing that believing in the Santa Claus. Santa Claus is not able to fly because of many reasons. Physical reasons. Okay, so how are we doing? So how many, let me take a look. How many answers we have? 70, 70. Eighty, 82. So that's really good because I remember, if I remember correctly, the first in-class quiz, there were 84 answers or something like that. So this is roughly the same amount. Oh, look at that. So it's getting better all the time. So maybe I should get started later in my classes, not at 4 o'clock, but say 5 o'clock, because there are more and more people joining in. Okay, 92. So success rate is what? 25. 25. 90. What the heck is this pain in my chest? Oh my God. All right, from this on, we need to make an agreement, like serious agreement, that we don't believe in Santa Claus, and we are not believing that the particle have a rotational degrees of freedom. Yes. Now you all say, you all have to do this. You have to do this. Yes. Okay. Let me see. So, but it's pretty nice, if you look at the overall picture, it's very good, very good. So we have here 94 that is saying that is interconnecting generalized coordinates. That's exactly what he's doing. So it's combining generalized coordinates. That's what he's doing. Okay, so we continuing that. Let me see where we are at. So you need to go all the way back where we started. So it was, where is it now? Still up further, this direction. This is what we discussed. All right, then comes a big pain. This comes very involving math. Here's what I'm proposing. I'm gonna take a look at this translational joint. And if you guys are not understanding me, that's fine. Think about something else. Like think what you're gonna do right after their lecture. Like, all right, I'm gonna go to the liquor store, and then I'm gonna go to grocery store. No, first the grocery store and then liquor store. You think that, and I will explain it, and then I will wake you up when we're done with the translational joint. How that sounds? And you don't need to go to the liquor store if you don't want, so that's okay too. Okay, I have here two bodies. I have beam-like body, that is called body A, and then I have a box-like body, that is a body B. And these two bodies are connected together via translational joint. You know what happens, this box-like body can slide along the beam-like body, and that's it. That's what it can do. It's going to take two constraint equations to set this, not more than that. And the one constraint equation is going to be very simple, another one will be very involving, very difficult. Okay, so let's get started from the simple one. The first one is that they have to have the same rotation in the space from this on. The rotation can still change, but they cannot be a relative difference between these rotations. So that's going to be simple. So the theta A minus theta B have to be equal to constant number C. Now if the system is rotated like it is shown here, C here is actually 0. So the relative difference between them is initially 0, and it remains to be 0 regardless what happens in the system. That's your first constraint. Not complicated at all. The second one is going to be the one that allows this sliding, this relative translational motion. How are we going to do that? So we're going to make it happen by setting two vectors, and setting these two vectors to be perpendicular with respect to each other. These are orthogonality configuration. And we're going to first make one vector that is getting started from the point O and ends to the point P. And that's going to be the one that connects body A and B. And then I'm going to have the vector H that belongs to body B only. And I'm going to set these two vectors to be 90 degrees angle with respect to each other. And that's going to be my second constraint equation. And I'm going to make a use of the dot product of two vectors and setting this perpendicular condition there. That's going to be my second constraint. All right, what is left? is these vectors. These vectors need to be defined. So the first one, this is a little bit how it's gonna go. So I'm gonna get started here, I'm gonna end here. So simply I just define this location and this location by using the only equation that again, that I'm familiar with. This one. And it's gonna be, this is where I started. This is the body A. And then it's gonna enter the body B. It's gonna be a little tight to write it, but you got it. That's gonna be the vector this direction, and then I'm gonna do the H, and then setting them to be perpendicular. All right, you see, this is really nice representation. So this is a vector that it's go to this point. And then I'm gonna set another vector that ends this point. There are two different bodies. I'm gonna use this Kinematics, the only one that I'm familiar with, and that's it. Second one belongs to body B only, so it's I can just make a use of the same equation, but because they are elementing, these ones are elementing each other, what is left is this one. Now the only math, the final math needed is to set this vector, this one, and this one to be perpendicular. This is how you do it. You have the dot product of two vectors and you're setting this to be equal to 0. This, by the way, is going to be scalar component. Because two vectors, when you multiply it like this, it's going to end up to be a scalar. So very bad looking mathematics. So when I look at each of these components, they look this bad. This K looks even worse than that. Eventually, it's going to be these equations. When I do this multiplication, this is how my constraint equation look like. How you can do it? Of course, with the help of symbolic math tool. So if you're crazy enough to try to do this by using pen and paper, I should penalize you to do it. You should, that of course you can make your life miserable any way you want, but not recommended. Not recommended at all, because a single mistake here in your pen and paper deriving are never gonna work out. Never gonna work out. Most of the stuff, in my team, we're doing quite a bit of math. Almost like 0 amount of pen and paper deriving, because what happens so easily that there's this one ridiculous mistake, and it takes months to figure out where is a mistake. Symbolic math tool is so powerful because it doesn't make that much of a mistake. Sometimes there's a need to these simplifications and such, which symbolic math tools are not able to do. But other than that, really powerful tool. Okay, that was now when you guys need to wake up. So we're back in the business, so we're back to look at the constraints. Okay, how you want to go? So should we first look how we can derive the constraint equation for this system? And then have a break, or would you like to have a break right now and get back to this mechanism? What's the way you want to go? So do we have a weak connection between me and you, or what's going on? Is the Wi-Fi not working, or why you guys are not communicating? You could just say yes or no. Okay.
Yes.
So you want to have break first and then come back.
Yes.
2 minutes. 3 minutes. 3 minutes. Because I'm a little hurried today, so I need to go back home fast. And okay. See you guys in 3 minutes. Hey, so in the YouTube there is this XP option. So what's that? XP. So if I click that, what's that? Is it like thumb up or what is it? So it's XP. So what's that?
You can check it by clicking.
Okay, so look at that. So if you know what the XP is, I still don't know what that is, but if I click that, it gives me the few students that are fan of this class. Completely new feature. I was not aware of this thing. So it's like XP is you can put yourself in the XP of the class. Don't ask me how you can do it. Okay, there are questions from online participants. One of the questions is that, don't know when this was asked, but in this example, can body A still rotate around body A? No, it cannot. No, it cannot. I think this was this translational joint example. Then there was another comment that, are we going to learn to use a symbolic math tool? No, you need to learn it by yourself, because those are self-explaining tools. They are not hard to use. They are pretty straightforward to use. You just open it, put the matrices there, multiplied matrices, and get surprised. It's going to do the job fantastically. Okay, XP, new thing that I learned. Nice, super nice. XP. Okay. No, they were artistic names, so not the real names. Yep. Okay. Let me think. We were. We were here, right? Okay. What's going to happen is that we're going to create the constraint equations for this system. How much this is different than what we looked earlier? Remember, we looked earlier at the mechanism that was like, not here, of course, but here, the mechanism that was like this. How this is different? Not really different. The only difference is that the primitive joint, this one here, is constrained slightly differently. But other than that, it's the same system, more or less the same system. Okay, so now you know this is a major advice to you for this one that is about to come, which is number of degrees of freedom. What's going to be the number of degrees of freedom in this case? And I'm going to, just a second, I'm going to allow you to answer this question. Okay, number of degrees of freedom. And I'm going to take myself back here. You know, take a look at how many moving bodies, how many translational joints, how many primitive joints. How much this is different what we looked a little while back? No difference. Well, let's say that there, let me correct myself. There is a difference, of course, because the way the primitive joint was oriented. But other than that, okay, you guys ready? So is this so you guys are somehow confused because of this? You shouldn't. Oh, okay. So can we take a look? Okay, I'm not going to move forward, but I want to take a look like how we're doing in this in-class quiz, which is going to be this one. 60, 68, 69, 70 answers so far. Okay, so it's going to be in 5, 4, 3, 2. Is it still counting? Yeah, it's still getting up. Okay, and I'm not going to close it, so it's going to be right. Okay, success rate 100%, 100%, absolutely 100%. Okay, there's no other way than 100%. 100% look like this. We're going the wrong direction. because remember what happened a little while back, we were scoring higher. I'm not going to repeat this anymore because soon we're going to go all the way down to their 0. So this is it.
I think A, C, and D are family members.
So what was that?
I think A, C, and D are family members.
Somebody's not the family member. We'll get back to you. Okay, but let me. Okay, so we have here 1, 2, 3 moving bodies. So that's a 6 generalized coordinates. So how many revolute joints? 1, 2. So that's going to be 2 multiplied by 2, 4, and 1 primitive joint. So that's 1 degrees of freedom system. It's the same. No difference. The only difference is that the primitive joint is oriented differently, but the number of constraint equations is not changed. Same. All right. Okay, so let's take a look how we can compute it. So let's get started from the point O. Okay, here comes a very important information because look where the point O is located at. So it's located in the center of the body reference coordinate system. Because of the center of the body reference coordinate system, is it then necessary to go this detouring and first travel the body reference coordinate system and then back? Can you just create the shortcut? Answer is, you are never ever allowed to take a shortcut. You know, what is not allowed in this class is thinking. Don't think. Because whatever you start thinking, you can see, hey, I can make my life easier. I'm just not going to go to body reference coordinate system and then back, but let me just, stay where we are and just constrain that. Not that. Always, always, always follow this equation. What this equation is saying. First, go to body reference coordinate system. Then rotate yourself, and then if the U bar is located here, then come back. First there, and then back. Okay, so that's what we're gonna do. So we're gonna take this R, this is unknown, and then the vector U bar, look where the X is pointing. So it's pointing downwards. So that have to be obviously minus L divided by 2, motion in a Y direction, displacement in a Y direction is 0. And now look what I'm doing. I'm constraining both X and Y to be 0. Because body reference coordinate system is located here. That's why. When I do the math, it's going to give me the 2 constraint equations. All right? Then I'm going to move forward. I'm going to look at the point P, which is common in a body A and body B. I'm going to reach this point using, again, this equation that I'm familiar with. 2 different ways. I'm going to set these 2 different ways to be equal. That's going to give me 2 additional constraint equations. 2 additional constraint equations. All right? So this is a variable. This is a variable. Vector U bar have to be, first of all, positive because you're moving along the local Y coordinate axis. This is 0, variable, variable. Here you have to go backwards. That's why it's a minus L divided by 2. You do the math, that's going to be 2 additional constraints. And the one more left is going to be this one here that is constrained such that the motion in the global Y coordinate axis is not allowed. Variable, variable. You just need to reach out this place by putting here L divided by 2, and then you're setting this motion to be 0. This one. When you do the math, that's your 5th constraint equation. All right, that's all about the constraint equations. Now we're going to discuss something that is way more difficult than anything so far in your life. And we're going to discuss about Jacobian. We're going to discuss about kinematic analysis. And we're going to see what happens if we have the matching number of generalized coordinates that is expressed in the terms of vector Q and constraint equations that is expressed by using vector C. So if this consists of 6, hypothetically, this is 6, how you can solve the response. You can solve it by using, again, kinematic analysis, but how? How you conduct the kinematic analysis, that's what we're going to discuss next. Clear? All right. Kinematic analysis where that is needed. I'm going to get back to the practical examples next week, but it's needed in analysis of workspace, then preliminary studies of mechanical structure. But there is a few examples where this is being used, and those will be introduced to you next week. All right, but how you do it? You have 3 different steps to conduct it. First, you need to get started for something that is called position analysis. Clearly, by far, the hardest step to take. This is not going to be an easy thing to do because this is going to be based on iterative procedure. Something that you have heard about it earlier, but probably never used in real life. We're going to make a use of that skills that you have learned bachelor level, first year or second year max. Now we're going to solve it using kinematic or making kinematic analysis. Then we need to move on. Then we need to do the velocity level analysis. It's pretty straightforward. It's a matter of substitution, nothing but substitution. And then comes the last level, which is an acceleration level. It's somewhere between this one and this one, medium level of difficulty. Okay. All right. So to take care of all the steps, the one is critical. First, write down the constraint equations associated to joints. That's once you have that, rest is more or less mechanical thing to do. All right. Yeah, this says once you have the constraints, rest is a boilerplate. Not really, because position level is still, this level is still a little bit of challenge. Okay, here's how it looked mathematically. You have a certain number of constraint equations that are a function of generalized coordinates, possibly time, but not necessarily. You have them NC number, because this is where this number of constraint equations is coming from. You can express them in a form of vector. You just put each of these equations in a vector form, like this. That is your vector C. Okay? And then what you're going to do with this vector C, you're going to solve this. And how you're going to solve it? This is going to be something that you have heard about it earlier. This is based on Newton's difference, sometimes called as a Newton-Raphson method. Basically, it is the way to solve these nonlinear algebraic equations. That's what it is. This equation, it's like generally speaking, you cannot solve them in a closed form. You just cannot, because the unknowns that we are really interested in are not explicitly mentioned, but they are hidden inside of the equations. And we know this because it's already like, remember the constraints are like Rx minus theta, something like that. So they are explicit. They are not explicitly mentioned, but they are inside of the equations. The only way to solve this is to use these iterative procedures, which you have heard about it earlier. I'm sure that you guys have heard about the Newton method, Newton-Raphson method. Have you not? Of course, because that's what they're teaching in your preschool. Not in a preschool, but in a high school, perhaps. I don't know if you do that. Maybe not high school. But anyways, in a bachelor level, for sure, there's a course about numerical methods. One of the basics, if not the basics method, is Newton method. This method is based on something that is called Newton difference. And what you need to do is that you need to compute this one, which is called Newton difference. This Newton difference is not the solution of anything at all, but is a way to solve the system. This is a direction to solve position level analysis. This is giving me the way how this original vector Q can be updated to get a better solution. And you keep on repeating this until you are reaching the level of accuracy that you are comfortable with. That's going to be the method behind. But we're going to take a look at the method behind momentarily. But there is this thing that I would like you to take a look. This is partial C, partial Q. This one is a vector. This one is a vector. This one here, partial C, partial Q, is matrix. Matrix that is called Jacobian matrix. Jacobian matrix comes along with the number of partial differentiation. Dimensions of the Jacobian matrix already tells you quite a bit about the structure of your system, because have to be square in size if you want to solve kinematic analysis, meaning that this vector C have to have the same amount of components than this one. Otherwise, it's not going to be square matrix. And you know what you need to do to solve this Newton difference is that you have to invert this one. You can only invert the matrix if it is square shaped matrix. Any other shapes, you just cannot. You cannot. You still alive?
Yeah.
You're still alive. I hear somebody's breathing, so it's okay. You still, everything is okay? Very good, very good. So you need more plot. I need more plot. Right, which is more map here, right? You got it. I'm going to give it to you more. So, yeah, I'm going to give it to you more. So, all right, so where this is coming. So this is coming from the way we're solving this equation is that we're adding this small difference, this Newton difference to the equation, and then we're going to use a Taylor series to solve it. And the Taylor series is going to go such the way that you have first this original equation, then you're going to have a partial differentiation of with respect to variable multiplied by delta Q, and then you have a higher order terms. What we are doing in the Taylor series is we don't care about higher order terms, so we leave it here. This is going to be something that we can solve. We set this to be equal to 0. This is where this delta Q can be solved. And it's going to be like this. This is how you can solve it. Like I mentioned earlier, this one here is going to be matrix that you have to invert. Here's another big reason to use a symbolic math tool, because inverting the matrix, no, pen and paper, forget about it. It's not going to be possible to do it, particularly the sizes that we are dealing here. So minimum is a 3 by 3. Maybe that you could, but the bigger than that, you cannot. You just cannot. This one here is called Jacobian matrix. Jacobian matrix. All good. Real good. Very good. Okay. Jacobian matrix, how this is constructed. It is just a partial differentiation of each of the components with respect to each of the components. What are each of the components? Vector C, vector Q. So it is a square-shaped matrix in the case of kinematic analysis. So the first row consists of partial differentiation of first constraint equations with respect to all the generalized coordinates. First the one, second, third, so on and so forth until the last one. Second row will consist of the second constraint equation, differentiated the same way. First generalized coordinates, second, third, and so on until the last one. And this is the last constraint equation, the same thing, differentiation after differentiation. So awful lot of partial differentiation, but nothing but partial differentiation. Makes sense? Okay, I mentioned this iterative nature. So once you're able to put up together a Jacobian matrix, you can compute this Newton difference. Newton difference is not your final destination, but it's like a GPS system. In a GPS system, you put a certain address to your map system, GPS system, and then it started to give you instructions how to move ahead closer and closer to your final destination. So what this is doing to you is giving the instructions how to update your generalized coordinates. You get the new set of generalized coordinates, then you're updating your Jacobian, you're updating your constraints. If you're close enough your final destination, it gives you this sign that you reach your final destination, meaning that when the delta becomes to be small, you can continue this forever, but you cannot gain much because this becomes to be insignificantly small. Typically is made in such a way that there's like delta Q, you compute the length of this one. When you look at the length becomes to be small enough, that's it. you reach your final destination, you're there. And you do this final destination until you reach the tolerance number. You keep on updating this over and over again until this becomes to be small enough. That's how it works. This was a position level kinematics. Position level kinematics. Position level kinematics. Okay, we still have to go with the velocity level and acceleration level, but let's practice first. Let's compute the Jacobian for this system, which is not kinematically driven. Why not? Because this is a primitive joint. This is a primitive joint. I have originally 3 generalized coordinates, 2 constraint equations, so it's a 1 degree of freedom system. Okay, how are these 2 constraints? They are the ones that I mentioned here. We computed them a few slides back. And what I'm doing is that I'm comparing the Jacobian for this particular system. Very, very, very mechanical. I'm going to take first constraint equation, this one here. I'm going to put it here. I'm going to differentiate that with respect to all the variables of the system. What are all the variables? They are the vector q. Vector q consists of generalized coordinates. How many generalized coordinates? 3. 3. Because everybody needs 3 generalized coordinates. Everybody needs 3 generalized coordinates. Okay, so these generalized coordinates are rx, ry, and theta. This is my unknowns. So what I'm going to do is I'm going to differentiate this with respect to my unknowns. These ones. Okay, first one, my first constraint equation differentiated with respect to this one. So when I do that, what's going to give it to me? 1. Nothing but 1. Then I'm going to differentiate this with respect to ry. Not mentioned here. Is not mentioned. So it's going to be 0. And then finally, I'm going to differentiate that with respect to angle theta. This is where the angle theta is here. So when I differentiate that, so it was originally L divided by 2 multiplied by cosine theta. When I differentiate that with respect to theta, not time, but theta, it's going to be given to me minus L divided by 2 sine theta. Clear. My first row, done. Second row, I'm going to take this constraint equation. I'm going to differentiate that with respect to same variables, very same variables. First with this one, not mentioned, so it's going to be giving me 0. Oh my God, this goes almost like in a rock concert. When I'm singing something like, then I stop, you continue. And then let's try this one more time. When I differentiate this with respect to this, I'm going to get what? Now I know what it feels to be a rock star. This is fantastic. All right, I think I just need to get a little bigger loudspeaker to make this to be real rock star style. All right, then this one differentiated with this one. That's too complicated. You don't need to sing it with me. So it's going to be minus L divided by 2 cosine theta. This is my Jacobian. Let's see if I take some stuff out. Is this a kinematically driven system? Is this kinematically driven system or dynamically driven system? Who's voting for kinematically driven? No one anymore, because we voted this earlier, so this is dynamically driven. How I know that? Because the Jacobian is not skewer matrix. It's not. How can I know that? Because it consists of 2 rows, 3 columns. If it would be kinematically driven, it will be 1 extra row, because I need to invert this one, and I cannot invert this, just cannot. Why? Because the dimensions are not invertible. I can only invert if it would be 3 times 3, so on and so forth. So I have to be square safe. This one, no way. Are we good? Good thing. Oh, we have no chance to survive here. Absolutely no way. So what is that the Jacobian matrix tells you? Okay, is it going to be a physical dimension of the body? Color of the body? Number of degrees of freedom? And then our all-time favorite, Santa Claus. Okay, and this is where we're going to close. Now, here's my big promise to you. You're going to go well with this in-class quiz. You're going to score 100%, or at least not voting the one that I hate the most. And then we're going to be friends rest of the life. Deal? Okay, let me correct, because I know that now you're going to intentionally vote it incorrectly. So we're going to have something fun next week. Better. Is it better? Way better. Way better. You're right. Success rate, we're going to, I mean, it would be, I would, now if we're going to score 100%, then I'm going to really cry because of the happiness. We'll see. And guess what's going to happen right after this? Once you guys are voted, then we're going to close for today. We're closing the class. Because like I mentioned, I have a business appointment at 6:45. I'm a little bit in a hurry to pedal back home. Okay, so we have 60, 67, 60, 70. So last time it was 80 something, 83. Okay, you guys all done? How many of you voted the option D? You better keep it as a private information if you did. Okay. Okay, 80, okay, this is it, 80, 82, 84. You guys want to see how the 100% look like? 90. Okay, now the last ones are not following the lecture, so we better close this because they... Fantastic. Not because of the 100%, but no one is saying that the rotation of the particle. So we're making progress. We are making progress here. Big time progress. Okay, guys, next week we're going to do something... we're going to continue with the story of kinematic analysis, and then we're going to move on to dynamics. Here comes Mustafa, so it's a time to close the lecture. You guys take it easy, have fun, and see you in a cafeteria with respect.